Good morning. Today I'll be presenting my design solution, a sustainable aquaponic system developed in response to my client's needs. The project follows the Creating Design Solutions process from the Victorian curriculum and demonstrates how design thinking, sustainability, and STEM concepts can be integrated into real-world solutions. The client for this project is a family friend who lives in an urban apartment with limited balcony space. They want to grow fresh vegetables at home, but face several constraints, including limited water supply, restricted space, and a busy lifestyle that requires a low maintenance system. In response, the design brief is to create a compact, sustainable aquaponic system that effectively produces food while minimizing space, water use, and maintenance. Existing solutions. To inform my design, I investigated existing solutions. Traditional aquaponic systems are often large and can require significant space, making them unsustainable for apartment living. The hydroponic systems are more compact but do not include fish, meaning they lack the benefits of a natural nutrient cycle. Soil-based gardening also requires more water and space. This comparison highlights a gap for a compact, efficient aquaponic system designed specifically for urban environments. Design options. I developed and compared these possible design solutions. The first option was a horizontal aquaponic system, which is commonly used but requires too much space for a balcony. The second option was an indoor system, which allows for controlled conditions but increases energy use due to artificial lighting. The third option was a vertical aquaponic system. This option maximizes vertical space, reduces water usage, and aligns with the client's needs. Based on the comparison, the vertical system was selected as the most effective solution. The final design concept is a vertical aquaponic system. It includes a small fish tank, vertical grow beds, a water pump, and a filtration system. Water circulates from the fish tank to the plants where nutrients are absorbed and then returned clean to the tank. This closed-loop system ensures efficiency and sustainability while supporting both plant and fish health. Materials and components. The materials and components were carefully selected based on sustainability, cost, and practicability. Recycled PVC pipes are used for the grow beds, making the system lightweight and environmentally friendly. An energy-efficient pump ensures water circulation, while LED grow lights support plant growth and low light conditions. These choices reduce environmental impact while maintaining functionality. System diagram. This diagram shows how the aquaponic system operates. The fish tank produces rich waste, which is pumped to the grow beds. Plants absorb these nutrients, helping them grow while also filtering the water. The clean water is then returned to the fish tank, creating a continuous cycle. This visual representation demonstrates how each component works together as a sustainable system. The implementation process involves several stages. First, the system is designed using the CAD software to create accurate drawings and measurements. Next, the materials are sourced, prioritizing recycled and locally available options. The system is then constructed and tested to ensure proper water flow and plant growth. Finally, a user guide is developed to support maintenance and long-term issue. Risk assessment and risk management. Several risks are identified during the design process. These include electrical hazards from the pump and lighting, water leakage using slip hazards, structural instability, and poor water quality affecting fish health. Identifying these risks is essential to ensure the safety and reliability of the system. To reduce these risks, several strategies were implemented. Waterproof wiring and safety switches are used to prevent electrical hazards. The structure is secured to ensure stability and regular monitoring of water quality, maintenance, and a healthy system. These measures ensure that the risks are minimized and the system operates safely. Sustainability and ethics. Sustainability is a key focus of this design. The system is used a closed-loop cycle to recycle water and reducing waste. Recycled materials are used wherever possible and food is produced locally, reducing their environmental impact. This aligns with ethical design principles and supports a responsible consumption and sustainability goals. STEM integration. This project integrates all areas of STEM. Science is demonstrated through understanding ecosystem and nutrient cycles. Technology is used in designing and managing the system. Engineering is applied in constructing the structure and ensures functionality. Mathematics is used for measurement, water flow, and system efficiency. These connections align with the Victorian curriculum and support worldwide learning. The success of the aquaponics system is evaluated based on its ability to meet the client's needs while maintaining sustainability and efficiency. Key criteria include space optimism, water efficiency, system durability, and the ability to support healthy plant and fish growth. The vertical design effectively addresses spatial constraints, making it highly sustainable for urban environments. Additionally, the use of recycled materials and a closed-loop water system demonstrates strong environmental responsibility. However, limitations include the need for regular maintenance and potential system failure if components are not monitored effectively. Further improvements could include automation of water monitoring and feeding systems to enhance usability. Overall, the design successfully meets the brief while demonstrating ethical, sustainable design principles aligned with the real-world applications. The development of the aquaponic system that is adapted to urban living tackles the difficulties of limited space and resources while also encouraging sustainable living for urban dwellers. Compared to traditional horizontal systems and hydroponics, this vertical aquaponics design is more space efficient and water conserving, making it more sustainable for urban environments. Not only does this prototype fulfill the requirement of the client, but it also functions as a model for more widespread uses in the urban environments that are comparable. This design integrates STEM through science, ecosystems, technology, system design, engineering, structure, and mathematics, measurement, and flow rates align with the Victorian curriculum. It is possible for aquaponics to make a sustainable contribution to the achievement of global food security and sustainable development goals through the use of innovation and sustainability.